Hi, everyone. Welcome back officially to MAT1841. So last time, we spent some time discussing an overview of the various topics that you might consider as things to do for your term project. So we talked a lot about these ML topics that I really consider sort of out of scope for this course, just because it's in so many other courses that you could be taking here at U of T. Today, I'm going to give a slightly slower, well, not that much slower, overview of basically the rest of the semester. So these are going to be the topics that I hope to hit in varying degrees of depth. I mean, it'll also depend on what people are interested in. And so if there is one of these topics that you really, really enjoy, you should let me know. Or if there's one that you really, really hate, well, if enough of you say you hate it and it's not one of my pet topics, then maybe I'll get rid of it. Maybe. No promises. But anyway, so what are the various topics? Well, let's go ahead and get started from current. So, well, we're going to be talking about random hashing. So this is actually going to be the topic of next Wednesday's lecture, or if we have enough time today, I have prepared notes for that for today as well. So what's the big probabilistic sketching and streaming, matrix decompositions, random graph theory, percolation theory, wavelet bases, some notions of complexity and entropy. Obviously, we're not going to teach all of information theory. That's an entire multi-course set in and of itself. Some nonlinear dimensionality reduction, and maybe some computational topology at the end to cap things off. So let's start with random hashing. What do I mean when I say random hashing? So some of you may have taken some computer science classes, and you might have this intuitive sense that a hash function transforms numbers into random numbers. What exactly does that mean? And what's the implication for what we want to do in this course? Well, as we discussed, real data has all kinds of unknown probability distributions. So like a lot of the goal of machine learning is to try to understand what the underlying probability distribution for real data is. But now, so that really brings up two different sort of not opposing, but complementary approaches to handling large amounts of data. One is to just try to understand the distributions it comes from. And so this is what I would largely classify a lot of traditional ML as. So what sort of distribution does your data come from? But another approach, which is very common in sort of like CS databases, is, well, we don't really care so much what the distribution it comes from. We just want to force it into something that we can manage. And so this class is mathematics of massive data analysis. And so like there are two things you can do. One is you can try to analyze it in its current shape. And the other is, well, you just force it into some shape that you want and worry about analyzing it later. And both turn out to have their uses. Hashing and projections are an example in some sense of forcing it into some particular distribution. So we saw that a little bit with like the Johnson-Lindenstrauss projection, where we were able to force it into a slightly different distribution, a lower dimensional one, while preserving some of the properties we care about. And in some sense, that's what we're going to do with hashing as well. We're going to force it into some other shape that has nicer properties for us to work with. So now, just going along with the intuition you might have from a computer science class, an idealized Oracle hash function is a function that maps a universe of elements uniformly into some target set. So here I have the interval between 0 and 1. If you're more of a computer scientist, you're probably like, well, we never actually deal with real numbers in computer science. Instead, you probably are trying to map to some finite field or to some finite set. Often the integer is mod to some k. But regardless, you're trying to map uniformly each item into some other set. You're basically randomizing it around in this target set. But of course, this is idealized because, well, basically what you're saying is that this random hash function is itself a random variable where it maps each of your items in your universe to some other random variable that has a uniform IID distribution. Unfortunately, storing such a random hash function, or even just computing it and writing it down, is really difficult and takes up a lot of space. So instead, can we approximate these idealized hash functions with less randomness? And so this is one of the key tasks in like the study of random hash functions, which we'll discuss either later today or on Wednesday, depending on how much time we have. Okay, but once you have these shaping functions, once you have these hash functions that you can use to shape data into these nice uniform distributions, we like uniform distributions, well, then you can do all sorts of clever things with data retrieval. And one example of this is these are often used for so-called sketching algorithms. So these are sublinear space algorithms. So how do you store large amounts of data? Well, maybe you store some approximation of that data that you can compute on. And so that's the whole point of these sublinear sketching algorithms. And you represent really big data probabilistically as smaller data. There's some sense in which you can think of Johnson-Lindenstrauss again as some example of that, right? You have some large amount of data to begin with, all these points in this high-dimensional space, and maybe the thing you want to compute is pairwise distances. Well, I mean, you could just store all the original data, and that allows you to compute pairwise distances. Or what you can do is you can store it probabilistically in a smaller amount of space by doing this projection down to this lower dimension. And we prove that you still usually preserve approximately the pairwise distances in your projected space. Okay, and you can do this for all sorts of different things, not just, let's see, yeah, so not just Euclidean distance, but you can do this for things like estimating the size of a set, estimating the different quantiles, so the distribution of numbers in the set, frequency distributions, set membership, the mode, so the frequent elements, things of that sort. And so these are all things you can store in a much smaller amount of space with some chance that you're wrong. And so that's sort of the point of these probabilistic sketching algorithms. And they're widely used in practice in like routers, databases, search engines, and et cetera. And I'm a computational biologist, so I also care about the fact that it's commonly used in some computational biology applications, which I'm not going to talk about too much in this course, but I just thought I'd throw this in there since that's my pet stuff. I'm actually going to spend some time. So unlike yesterday where we just swept through everything, I'm actually going to spend a little bit of time just explaining these different topics. So let's start with a very simple problem. Excuse me. How many distinct items are in the list? So if I hand you a list of objects, how many items are in it? What method do you have of figuring that out? Yeah. Okay, yeah, so you're already jumping a step ahead. But yeah, so the basic idea is, well, you can just count. If you have some way, if you want to count unique items, well, you can just hash everything to some to your hash table, and then you can deduplicate pretty quickly that way. But now, let me propose a slightly different way. This is going to be a really weird way of counting the number of items in the list. I am going to use hash functions again, but instead of storing an entire hash table, because the hash table, you need to store as many items as your original list, right? So instead, what I'm going to do is I'm just going to store the smallest number. So if I have two items, I'm going to hash it to some random variable between 0 and 1, and I'm going to store the smaller of the two numbers. Now, in expectation, the number you're going to store is going to be about 0.33. It's going to be about a third. You can just sort of think about this. If you place two numbers randomly on the unit interval, well, chances are the smaller of the two is going to be about a third of the way in. But if I do this with three numbers, chances are it's going to be about a fourth of the way in expectation. Obviously, these numbers could be anywhere since these are all random variables. And if I have nine numbers, then it's about a tenth of the way in. And so what you can do instead is you can insert, I just store one number, and that gives me an estimator for how many total items are in my list. And because I'm using a hash function, I also don't count duplicates in the same way that I would for hash table. So basically, by transforming my list, it can be a list of arbitrary elements into a series of uniform random numbers between 0 and 1. I know something about the minimum of a bunch of uniform random numbers between 0 and 1. We can explicitly compute the probability density function and compute the expectations. And it turns out to just 1 over n plus 1. And so by storing one number, I have an estimate for the overall size of the set. Of course, if you store just one number, your estimate's going to be pretty bad. But if you store 10,000 numbers, if each one is an estimate, you end up with about a 1% error rate by just storing the smallest number each time. Does that make sense? So this is the basic idea behind the count distinct sketches, which is, well, just store the smallest number of your hash. You don't care about anything else, and this gives you something that takes about O of log n bits of storage. Because, well, I'm saying that I'm mapping these things between 0 and 1, but really what I'm doing is I'm mapping it into some specific. I'm really hashing into some integer, and then in some range. And then I'm dividing it by the total range of the integers. Yep.
Just to double check, so we hash everything between 0 and 1, and then we check the smallest number to use that to estimate how many.
Yeah, exactly. So you hash everything between 0 and 1. I mean, in practice, you don't hash between 0 and 1. You hash between like 0 and 65,535, and then you divide by 65. Yeah, the usual way that you would approximate a real number between 0 and 1 with a finite approximation, basically.
So do we use this technique because, like, sometimes in real life, a set is too big, like you can't count it directly, so you hash it?
Yeah, basically. So sometimes the set is too big, and so if your set is too big, you might instead of storing the entire set, because like the hash table does work if your set is small. You just store all your elements and you check to see how many elements you have. But if you have too many elements, like you might run out of memory. So instead, you just store the smallest number. That takes constant space. I mean, not actually constant. If you want a reasonable error, it takes 1 over epsilon squared error, where epsilon's your error. But basically just by taking an average of a bunch of things and then taking the standard error of the mean. But now, so how much space do we need to do this? Well, in order to store the smallest number, you need something on the order of log n bits of storage, right? Because you're trying to store the number 1 over n plus 1. And if you think about just storing, that means that you need to store at least, if you think about these as integers, you need to be able to store at least n plus 1 in terms of size, and so that's log n bits. There's some constant that you need to add to it so that you, some constant factor, but it's not usually that big. And then of course, another factor that is your approximation. But each of your guesses only takes about log n bits of storage to keep track of. And therefore, you're able to find a number of distinct items in the list in log n space, well, times your approximation error. Okay. And this is, in fact, you can actually even do better than this. So here we're using O of log n bits of storage per like estimate, and then we had to keep like 10,000 estimates. You can actually do even better than that. And this is the really cool log counting, which were promulgated by Flageolet et al., et cetera. And it turns out that, well, if you think about these numbers, you only care about the smallest number, right? So you don't care about all these big numbers. Like you're very unlikely to store 0.7 as one of your minimum values, right? Because once you have a few items, it's very likely that the number you're storing is going to be smaller. And so it turns out that you actually don't even need to store the actual minimum number. You just need to store the order of magnitude of the minimum number. So you can think of this as taking the logarithm of the minimum number and then storing that value. And this is just another estimate on top of that. And it turns out that the math is a lot more complicated. You can't just compute expectations as easily. But when you do this, you only need to store the minimum order of magnitude to get a good estimate. So you can even further compress these hash values and just store effectively the exponent, so log of the minimum value. And so then you only need log n bits. So just to show this a little bit heuristically, if you had these objects in the set, we're assume they're hashable objects. Each of these you hash to some number between 0 and 1. I'm going to write it out in binary. So this is just the binary expansion. And then I take the minimum value of all of these. And then I just take the minus logarithm of the minimum value, which is equivalent to the number of zeros for the first one, just the order of magnitude of it. And you store all those values. And with some correction terms, you get errors that are on the order of 1 over root k, where k is the number of buckets. So you get the same, roughly the same error. The estimator is a lot more complicated, but you can get roughly the same error while using these sorts of, while only storing log bits per bucket. This is used in practice. This is one of the workhorses of like, well, large data analytics. But you only need of log n space, which is the really cool thing. So basically what we're doing is we're, by allowing ourselves some amount of error, we're able to significantly reduce the total amount of storage space that we need in order to compute any of these, in order to compute these quantities that we care about. And the other really cool thing about this is that these sketches are often composable. And so if you take the HyperLogLog sketch of a set A, and I take the HyperLogLog sketch of a set B, if we combine those two together by just taking the orders of magnitude and just like taking the maximum of the orders of magnitude, then what you get is the HyperLogLog sketch of A union B. And so this allows us to do all kinds of set operations, including figuring out the union size, obviously, between two sets, but also we can compute estimates for things like intersection size and stuff like that. Though the intersection size estimate is going to have large error if your sets are big and the intersection is small, as you would expect. Okay, was that all? I'll take a breather for a moment. You should ask me questions now.
So we have a list of things and want to figure out how many distinct ones there are.
Yes.
And what we're going to do is we're going to do, like, okay, that's, we just pretend there are like numbers already, and then we just go through them and then we find the minimum. Like,
Yes. Yeah, that's exactly right.
and then
somehow the 1 over the minimum is approximately the size of your set.
so we're saying this is like faster than if we were to.
It uses less space. And it is sometimes faster, but basically, how much information do you have to store? So if you were storing every single one of these numbers in your list, you'd have to keep track of, well, your entire set, right?
So we don't want to know what the object wants.
We just want to know the total number of objects.
Then why don't we just store the total number of objects? Why are we storing?
Because how would you store the total number of objects while not counting repeats? So if I give you a bunch of numbers and I stream them in, there are way too many numbers for you to store in memory. So there's no way you can write down all these numbers. I'm just giving them to you at 1,000 a second. Yeah, exactly. And so in that case, well, if you had infinite memory, you could just write down every one of these numbers, put it in the hash table, check to see if you've already seen it. If you haven't already seen it, add a new entry, and just count the number of elements in your hash table. But this doesn't work if you don't have enough space to store everything. This also has a couple other advantages. One of them is, suppose you have a big set, and suppose I have a big set. Well, if we want to know how many numbers are in both of our sets together, well then, if we want to do that exactly, we'd have to send, or one of us would have to send the other person our entire set. And so that involves a lot of communication, because that's the only way of actually deduplicating the set is to, well, know the entire set, right? But with this sort of method, you don't need to explicitly deduplicate it. Instead, you can just do this approximate thing and that gives you the union cardinality between these two sets. Okay, does that sort of make sense? So the basic premise of these sketching algorithms is our data is super, super big, right? Like this class is about massive data analytics. Our data is too big for us to work with. So can we come up with small compressed summaries that we can work with? And this is just an example of a small compressed summary that allows us to figure out the total number of elements, even if you can't store the original set.
Oh, sorry, where does the first log n come from? Like, why is log n bits?
Oh, because if you're going to store the number 100, you don't need to store 100 bits, right? So if you want to store, let me just write this out. If you want to store, let's say, oh, come on. If you want to store, say, the number 7, how many bits does this take this to store? Well, what is 7? It's 111, right? So if you want to write it in binary, basically. So it takes, you need log of 7 bits, log base 2 of 7 bits. Yeah, but because like we're storing everything in binary on the computer. And so the first log factor is, well, like if you want to count to 1,000,000, you don't need space 1,000,000 to count up to 1,000,000, right? You just have a counter and that takes log 1,000,000 space in order to count up. Yeah. But yeah, it's good that he stopped me, because this particular segment involves both a lot of probability and a lot of computer science. And so you should let me know if any of it's confusing.
So where does the second log come from?
Oh, the second log. The second log comes from the fact that instead of storing, so if we want to store this number, that would take 5 bits, right? Yeah. But we're only going to store the number 5. So instead of storing the actual number, which is 0.0000100 whatever, we're only going to store the number 5. For basically the log, we're only going to store the logarithm of that number. And
first you need a log 5 bits, right, to save that number.
Yeah, so this number here you can rewrite as 101. So it's going to take 3 bits to store the number 5.
Oh.
Yeah. Basically, we're taking several different logarithm operations. One of them is just like whenever you store any number in binary, it takes log of that number of bits. The second thing we're going to do is we're not even going to store the number. We're only going to store the order of magnitude. So if you think about writing it in scientific notation, all we're doing is we're storing the exponent. You're not storing the actual number anymore. And it turns out, and this is actually kind of hard to prove, so we're not going to prove it today. We may prove it in a couple of weeks, that you don't actually even need to store, you only need to store log n bits per bucket and to give this estimate.
So to make that worse, you keep taking, like now, say you want to store just the number of bits it takes to store 5, like if we keep going.
Oh, so the question is, can you do even better than this? Do you actually need log n bits? So it turns out that there are a couple answers to that. The first answer is that no one cares because log is so small that no one in practice needs to worry about the difference between log and log. The second answer is yes, actually. So there are even in the theory literature, there are examples where you can use only a constant number of bits per bucket and then just store a single other log counter. And you can still do this estimate with about the same asymptotic errors. I don't think anyone uses that in practice because the difference between a log bits, which is about 6 bits for any number that we would care about in our world, because that's 2 to the 64. You can store numbers up to 2 to the 64 with just 6 bits per bucket. And the constants are around, well, they're not that much bigger than 6, or not that much smaller than 6. There are not many constants that are that much smaller than 5 or 6. And so it doesn't actually matter in practice to decrease it. But yes, you can actually do it in a constant number of bits per bucket, as well as an auxiliary log bits. Note that I'm sort of waving stuff under the rug here, which I might mention later. I'm just sort of positing the existence of a magic hash function. And if you actually worry about the theory, if you're actually worried about the space complexity, storing the hash function actually takes a lot of space as well. In practice, we just sort of ignore that because we're oh, well, hash SHA-1 or whatever is good enough. But these are all considerations that you would do if you were a CS theorist, which we are not in this room right now. So yeah, what's up?
Each of those buckets corresponds to a different hash function.
Yes, let's use that as a first order approximation. Yeah, so that will work, and that's a much easier way of thinking about it. Yes, it turns out that there's a clever way you can use only one hash function and partition your items into these buckets, and that saves you a lot of computation time and gets you the same estimate asymptotically. Now, there are all sorts of additional things you can do, but the basic idea is you can think of this as independent estimates. Okay. Let's move on. I figure out while we're on this topic, since I really like sketching, I'm going to mention a different sketch, which is the sketches for the Jaccard index. So a moment ago, we were able to compute union sizes, right? And from that, you can compute the intersection size, but you have a big error if your sets are much bigger than the intersection. We can also directly estimate the similarity between two sets. So the intersection size divided by the union size with another sketch. And then if we wanted to, we could combine that with our union cardinality sketch, multiply them together, and then that would give us the size of the intersection between two sets. So remember yesterday I talked a little bit about Google and how search engines are great because they organize the world's information and all that. But I swept a bunch of problems under the rug, right? So now if you're a search engine, one of the things you want to do is you want to find pages that contain a particular search term. And the other thing you might want to do is you want to find pages that are important. But one of the things you might have noticed, if you've ever been on the internet, is that sometimes when you search for pages, you have a lot of copies of the same page. So they're all basically the same. You might have seen that there are a bunch of basically mirrors of Wikipedia, on the internet because it's free, and so people copy things around. But now, if you're a search engine, you may not want to have all of your results just be copies of the same page. Well, that's not very helpful, right? So how do you prevent that from happening? So if they're exact copies of the same page, well, that's easy, right? You just hash it and you're oh, well, I've already seen that page. I don't need to. But chances are it's not going to be an exact copy. You're going to there are going to be slight variations. Maybe a timestamp is different between the two pages. And so you can't just do an exact hash of the entire thing. However, if you could somehow figure out the similarity between two different pages, well, then you could filter it out that way. And so this is what Andre Broder did at Alta Vista. I don't know how many of you are young enough to remember Alta Vista, But it was one of the various search engines that got killed by Google, basically. There were many search engines that once upon a time. Now there are relatively few. But at one point, there was a search engine called Alta Vista, and they were trying to organize information, and they wanted to not repeat the same web page many, many times. And so the trick they figured out is, well, if you break up each web page into just sets of phrases, if two web pages have almost all the same sets of phrases, then, well, they're probably the same, and we can just filter those out. So now we have a set theory problem, right? How do we figure out the intersection between two sets? And we want that intersection to be really high. Or sorry, we don't want the intersection to be really high, because if the intersection is really high, that means that the two pages are probably almost identical. So let's think about two sets A and B with some overlap here in gray. So the white and the black dots with the overlap in gray. So now, if I had a way of doing a random permutation of my set, well, I might randomly permute my set. And if you think about the permutation, that's basically an ordering on the set. And so I can look at the minimum value, again, the minimum value under both permutations. So in this case, after list permutation, the minimum value for A is this gray element, because that's in both sets. And the minimum value for B is this black element, which is the first one. So they're not the same. But if you do this a number of times, what is the chance that the two minimums are the same?
So are you implementing the union of the two sets, or the?
I'm doing a permutation on the union of the two sets right now.
And you're taking the two smallest elements?
I'm taking the smallest element within each of your sets. So the smallest element in A in that set, and the smallest element in B in the union. And then my question is, how often are the smallest elements in A and the smallest element in B the same? So if you look at the way I've drawn it, when are they the same? They're the same whenever a gray element is at the very far end, right? And so the chance that two elements are the same is precisely the size of the intersection divided by the size of the union, because I've just randomly permuted things around, right? And so then if one of the gray elements happens to be at the very end, then that means the minimums of A and minimum of B are the same under the permutation. But if they're different under the permutation, well, then that means that the smallest element is not one of the gray elements. Okay, now, but how do you take a permutation of a set? Like, we don't necessarily have the union, but this brings us back to hash functions. So you can think of a hash function as an arbitrary ordering on the set, right? Because it's assigning a particular number to it, and you can just order by the hash function. And so basically the way you actually do this is you take the minimum hash values of two sets, and the minimum hash values for two sets, if you use the same hash function, they're equal precisely if with probability equal to the Jaccard index. So the size of the intersection divided by the size of the union. And so if you do this 10,000 times, then you get, roughly speaking, a 1% error in your Jaccard index. And so it's the same kind of trick, except you're doing it for a slightly different application. And the question is, how many bits do you need? Well, if you're doing a permutation, well, permutations are hard, but instead you can just store a hash function and store the hash value. And if you just store the minimum value, it takes log n bits.
Wait, you said we take the permutation, and then what are we doing?
Oh, we were taking the permutation, and then we're looking to see. So once you've done the permutation, think of the left as small and think of the right as big, right? So you can think of ordering your permutation, right? And so what is the minimum A element in your permutation? Well, in the first case here, the minimum A element is there. In the second case, the minimum A element is there. And in the third case, the minimum A element is there, right? And then what's the minimum B element? And then we're asking when those match. And those match precisely with probability equal to the Jaccard index. And so because that's true, that means you can estimate the Jaccard index by doing multiple hash functions and then just looking at the proportion that the two are equal.
So is the error like approximate, like linear, like 1 over because of how many like trying to do this? Is like the error you get if you want to get like 1% error, you say you do it 10,000 times.
Roughly speaking, yeah. I mean, it gets slightly weirder because error is weirder because these are basically Bernoulli random variables. So basically, you're estimating the parameter of a Bernoulli random variable. Like that's what we're doing here, right? So you have a 0, 1 random variable and you want to estimate the expectation of it. And in fact, that's exactly what we're doing. And if you use hash functions, instead of storing a permutation, which is hard because then you have to permute everything, you just store the hash function, you store the hash value, that's a single number in, which is roughly speaking log n bits, order of log n bits, because that's how many bits you need to not have collisions, basically, right? I might go into this a little bit later. Oh, I have a worked example. I forgot I had this. So if you had one set that had 5 million elements and another set that had 10 million, you do your hashes, and then you look to see when the two are equal. And if those two are equal, you just estimate the Jaccard index as 2 divided by 7 if we had 7 iterations. And another nice thing is you can merge sketches because we're doing the exact same thing. You're just taking minimum numbers. And so this is the MinHash sketch. It's also used a lot in practice. So these are all set membership things. Oh, one other random note. Does it matter which element I choose to look at? You're always looking at the minimum elements in these sorts of MinHash or like the log-log counter schemes. You're always looking at the minimum one under some random permutation. And what that means is something we'll define a little bit more carefully in later lectures.
So like choosing min versus max is arbitrary.
Oh yeah, no, the min versus matches are arbitrary. Yeah, so that's completely arbitrary. Whether you call it a min or a max or like whatever, like min and max are arbitrary. You have to be a little careful if you choose like the 5th element or stuff like that, because there are weirdnesses that happen there. And sometimes you might want to, but that's significantly more advanced.
Why was the minimum element being permuted?
Oh, because we're defining the minimum under a permutation. So I have a bunch of balls, all labeled. I mix them around and then I roll them out, okay? And so then I say, well, which is the thing that's rolled the furthest? Yeah, and then I do it again. And which is the thing that's rolled the furthest? You might be wondering, why is it that we need log n bits for this MinHash sketch, but we only need log bits for the HyperLogLog sketch, even though they were really quite similar? And the answer to that is you don't, but the proof is a little bit more complicated. So you can't actually do this in log bits, and that's one of the things I proved a couple years ago, actually. But anyway, let's move on. So there are other types of streams. I won't spend too much time on this. I don't want to spend this entire lecture on sketching and streaming, even though I have a lot of slides for this. So another thing you can do is maybe you want to know if you have there are different types of like data models. So one is this turnstile stream, which we've sort of been talking about. You have a really long vector, and then you stream in a bunch of updates to this vector. Maybe you started with a 0 vector, and then each time I say, add 5 to coordinate 6, or add 3 to coordinate 1, or add 1 to coordinate 100. And then, so obviously you could store, if you could store this entire vector, well, then like you would know the vector at the end of the day. But what if you don't want to store this entire vector because it's really big? Well, and you might have several other questions about it though, like, well, what is some function of this vector after it's all done? After I've streamed all the elements without needing to store the entire vector to begin with. There's some sense in which this is basically what we've been doing with set membership, except now we've generalized it to, well, not just 0, 1s. So set membership you can think of as a 0, 1 indicator, whereas with these other streams you can think of them as, well, just adding values to some big vector. You might want to compute like the norm of your vector after you've streamed all your elements, or things of that sort. And there are also sketches for these kinds of things. And these should actually look quite familiar. So if you think about it, we were basically building a sketch for the Euclidean norm when we were doing Johnson-Lindenstrauss, right? So that was effectively what we were doing when we were taking these Gaussian random variables. Now, it turns out that there are other, I mentioned at the time that there are other things you could do for these sorts of projection matrices. And one of them is this AMS sketch, which allows you to compute the Euclidean norm using plus or minus 1 random variables. I mean, appropriately scaled. And after you multiply all your entries in this way, it turns out that you end up with an estimator for the Euclidean norm of the actual vector you care about. Okay, enough sketching. That's probably overstayed the welcome. Don't worry, we'll go into it in detail in a couple weeks. So there are a couple other things that, so I know some of you mentioned that you already learned about SVDs. If you haven't, you should, and you're taking 1850, you should learn about them within the next month or so. But there are all these different matrix factorizations, right? So what is a matrix factorization? So a matrix factorization is basically just you have some data matrix, and you want to write it as, well, as a product of smaller matrices. Did I get the dimensions right? I think I might have gotten the dimensions wrong. But anyway, you sort of know what I mean. So basically, can you write a matrix as a product of smaller matrices and basically encode the information of this big matrix in a bunch of these smaller matrices that are easier to store and that tell you something about the structure of your original data? And this is one of the things that SVD can do. So if you have a matrix that is low dimensional to begin with, that is a low rank to begin with, well, then if you use an SVD, well, many of your singular values will be 0, right? And so if your singular value is 0, you don't actually need to store one of the singular vector corresponding to it in order to reconstruct the original matrix. And so we can store these. So there are these. So when you have an actual low rank matrix, well, you can often decompose it into a product into an outer product of vectors, effectively. But now the question is, when you do this sort of thing, sometimes you don't get exactly you don't have exactly a low rank matrix, but you have a matrix that's almost low rank. So if you think about like an SVD, you might have an SVD matrix that is almost low rank, except you just added noise to everything. And you might want to, with an SVD, you can still get rid of some of that noise, but basically getting rid of the lower singular values. But now, this is super helpful because it gives you basically a lower dimensional understanding of your data. But in some cases, you don't. The problem with SVDs is you have negative numbers. And negative numbers sometimes make sense, but sometimes they really don't make sense. Oh, come on. Oh, is this doing? Oh, there. Okay. So, for example, if our data matrix is a topic modeling matrix, so this is an actual like real world example where you have n different documents. So like n different, maybe n different lab reports or something like that that you've written, and you have are different topics, and some of your lab reports cover certain topics and some of them don't. And so your documents are all a mixture of these different R topics. So maybe one of them is biology, another is math, another computer science, and some documents are, each document is a mix of some amount of biology, math, and computer science. Well, we want to be able to determine A, what topics exist, as well as B, for each individual document, what's it a mix of. But now, in this sort of framing of things, well, you might think, well, if I took an SVD, that might give me something like that, because it's basically a low-dimensional representation of our big, matrix of the documents and topics. So, like, it turns out that often there are particular combinations of topics that are more common. Like maybe math and CS go together more often than math and biology. So this is sort of the schematic. So you have this document by term matrix, and you want to come up with these topics. And so these topics are based on the words that are, or words or phrases that are in each of your documents. And you do this sort of matrix decomposition in order to get, figure out what these topics are, because the topics will be, well, here. Does that sort of make sense? You're decomposing a big matrix, and then when you multiply these two matrices on the right together, you get back your original matrix. But in the process, you've sort of defined each of these topics. Now, who can see? Well, the problem is when you use a standard SVD to do this, you might have negative numbers. And what does it mean to have a document that is minus 0.5 biology? Like that's just no longer a meaningful statement, because sometimes in real life, negative numbers don't make sense. Sometimes they do, but sometimes they don't. And in that case, you might want to have a matrix decomposition that, well, is non-negative. And this turns out to be a much, much harder problem than SVDs. SVDs have all sorts of nice properties. They're related to eigenvalues and eigenvectors and all that. But if you want to find these non-negative matrix factorizations, that's a much harder optimization problem. And in many cases, is actually NP hard. But there are approximation heuristics you can use to get close to a non-negative matrix factorization. And that will be something that we'll discuss when we talk about matrix approximations. Any questions about that? Oh, all the things that I just said. Okay. Another thing, so moving away from the sort of super CS-y side of things, which there is some fraction of, let's talk a little bit about random graph theory. So this is another one of the topics that we're going to cover, and it has some really nice like asymptotic mathematical limiting behaviors. So networks do often appear. So we mentioned this briefly when we talked about the sort of ML side of things, and we talked about like networks and doing graph partitioning, right? So like somehow you can have networks of electrical grids, social networks, protein interaction networks, and you can look at that. You can look at that real data, and you can cut it into pieces and understand the different components of your network. On the other hand, well, sometimes so you might be interested in modeling the generation of a network itself. So you might come up with some mathematical process that generates a random network, and you just want to understand what happens. Because maybe this generation process is related to a real world network, or maybe not. Maybe it's just some process that you care about. So let's start with defining a couple of these random graphs. The one people always normally work with to start with is the Erdos-Renyi random graph. So and this is a very simple graph model. Basically, you start with a bunch of points, a bunch of nodes, and then you randomly put together edges. So between every two nodes, you have some probability of having an edge, and that's independent. And so you can apply, because this is a random graph, even though this is a combinatorics problem, you can use a lot of the probabilistic tools that we did in the very first lecture to understand what happens. So like, for example, what's the degree of this, the average degree of the nodes? Well, the average degree of the nodes is going to be about NP, because each node has n different possible neighbors, well, n minus 1 different possible neighbors. And for each of those n minus 1 possible neighbors, it has a p probability of having an edge between them. And so you get a concentration bound on the degree of each of these nodes. So that's not too exciting, right? Let's just like, okay, well, fine. That's just the linearity of expectation. But more interesting stuff happens at a global scale when you have these sorts of random graphs. So how many connected components are there in this random graph? Well, if you think about the sort of at one end, you have 0 connected components, right? Because if the probability of having an edge is 0, sorry, you have n connected components. If you have a probability of 0 of having edges, so each like node is its own component. And at the very other end, well, when the probability is equal to 1, then you only have one connected component, right? Because everything's connected to each other. But now, when do things connect? And it turns out that there are several different phase transitions that happen as you increase the probability of connections. And so like it doesn't go nice and linear. It's not like, oh, well, when your probability is 0, it doesn't go like as the probability goes to 1/2, well, then you have n over 2 connected components. That's n over 2 or 2. Anyway, that's not how it works. Instead, what happens is there is a sudden sharp transition. So these are things called phase transitions, where all of a sudden, as your probability goes above a certain threshold, with overwhelmingly high probability, everything gets connected. So you can sort of think of it as like when you start off with a graph, you might have these little pieces to begin with, and they start forming, but then all of a sudden everything crystallizes together and everything connects in one fell swoop as the probability of edges increases. And this has applications in CS, but also interesting applications in material science. So suppose you have an alloy of an electrical conductor and an insulator. Like, I don't know, maybe you have what's an electrically conductive material? Iron. And what's an insulating material? Carbon's an insulator, right? No, it's not always an insulator. I'm not actually a material scientist. But suppose you have two different types of atoms alloyed together, and one of them is conductive and the other one isn't. So long as you have some path from one end of the cable, so maybe you have some big cable, and it's because it's wide because, of course, you have, it's wide in terms of the atoms. And then the question is, can you find a path from one end to the other? And if you can find a path from one end to the other, then that means that, the overall cable is still conductive. But if you can't find a path, if there is an entire, let's choose a different color. So if there's, for example, a bunch of the insulator blocking it, then all of a sudden that breaks this. And so you're no longer conductive. When this is conductive? Well, it turns out that you can model this. So like as you put in more insulator, so maybe the insulator increases the strength of your alloy. And so maybe it has other materials properties that you want. How much of this insulator can you put in before all of a sudden the entire cable is an insulator as opposed to a conductor? And it turns out you can model this by thinking of this as a random graph problem. So you can think of this as, well, if for a super simplistic model, you can assume that every single one of the two types of atoms take up the same amount of space. And what you're left with is basically a grid, some kind of grid in high dimension, well, not in high dimensions, in 3 dimensions. So you have some sort of a 3-dimensional grid, and some of these, and everything is connected to its neighbors, but some of these things are empty. Like this might be empty, that might be empty, and this might be empty. And then the question is, is this still a connected graph? And so this is precisely, this has the same kind of phase transition behavior as these Erdos-Renyi random graphs. It's obviously a different model for a random graph, but you can get these same sorts of phase transitions that, rubber, yes, that's a good example. Yeah, but so you can model this using the same types of, you can analyze it with the same kinds of phase transition tools to see whether or not the entire graph is connected. And so there are a number of different problems in this sort of regime that we'll be talking about. And of course, there are a number of different other models for random graphs. So note that social networks, which is another one of the popular places for graph theory, real social networks do not look like Erdos-Renyi random graphs. Why is this? Well, because when you look at real networks, if you look at the degree distribution for an Erdos-Renyi random graph is of course binomial, because that's how we've defined it. But real graphs in social networks tend to have this parallel distribution, which is very different. And so clearly, using an Erdos-Renyi random graph to model social networks is wrong. And so one of the other tasks in sort of this random graph theory, the more applied random graph theory, is trying to find models of graph generation that approximate the statistics of real-world networks. One model for building these sorts of social networks is a model called preferential attachment, where as you add new nodes, it's more likely to connect to nodes that are already popular. And so I am using popular in the social sense here. It turns out that if you're popular, you're more likely to get even more friends. Whereas if you have no friends, well, you're very unlikely to make new friends. The rich get richer. Yeah, so there are a number of other networks whose properties you have trouble approximating. And there are a number of other techniques you can use to try to generate graphs that have the same distribution as some real world graph. Another one of them is if you just want to preserve the degree distributions of a graph, one of the things you can do is, but you don't want to, you want to generate a new random network with the same degree distribution. One thing you might try is just start with a graph that you care about, and then cut all the edges in half. And so every one of your nodes is going to have a half edge, and then randomly rewire it. And so this is another way of preserving degree distribution, though you might lose some other properties. For example, connectivity gets completely messed up when you do this, right? Because if you happen to have a 2-component graph and you did this random cutting and rewiring, then all of a sudden it becomes a 1-component graph. And so you have to figure out what characteristics you care about preserving, maybe it's degree distribution, maybe it's number of connected components, whatever, and then build some model for generating a new random graph based on what you care about. Oh, and this happens to be used in the modularity clustering algorithm that I talked a little bit about yesterday. Okay, any questions about random graph theory? I think that's all I'm going to say about random graph theory. It has a lot of really fun phase transition type behavior and asymptotic limits. So there'll be some nice proofs there. Okay, well, let's talk about another fun topic. So many of you will probably have heard of the Fourier transforms, or at least I hope you've heard of Fourier transforms. They're pretty popular, but those give you a basis effectively in terms of sines and cosines for the space of functions, right? So any function you want, you can approximate to by just combining together a sum of a bunch of sines and cosines in some limit. But there's an issue here, which is that each of your basis functions contains information. Am I running out of time? Oh, it is. Wait, it's 4 already? Oh, wow. Okay. Clearly, I am terrible at keeping track of time. I will come back to wavelets and persistent homology and low-dimensional projections on Wednesday. So thank you so much for bearing with me. Sorry I got distracted by sketching and streaming, which is one of my favorite topics. And I will see you on Wednesday. Yep. Sorry about that, everyone. Bye, everyone in Zoom as well.